You hear black holes swallow everything. Nothing escapes, not light, not matter, not information. That was the rule until one physicist ran a calculation that broke physics itself. September 1973, a cosmology meeting in Krakow. Stephen Hawking wheels into a room of theorists and meets Yakov Zeldovich, architect of the Soviet nuclear program. Zeldovich and his student Alexei Starobinsky show him something impossible. Rotating black holes emit particles, spontaneous radiation from objects designed to trap everything forever. Hawking listens. He is 31 years old, 12 years into a death sentence called motor neurone disease. His body is failing, but his mind burns white hot. He returns to Cambridge with a problem gnawing at him. Can black holes really radiate? If they radiate, they have temperature. If they have temperature, they have entropy. And if they have entropy, every law of thermodynamics screams that they must emit heat. He attacks the problem from quantum mechanics. Virtual particle pairs flash in and out of existence everywhere in space. This is standard quantum field theory. But what happens at the event horizon? What happens at the boundary where space-time curves so steeply that nothing should escape? Hawking applies quantum field theory to curved space-time around a collapsing star. The math is brutal. He works through the equations night after night, running calculations through his mind because his body can no longer hold a pen steady. He finds something that annoys him. His own results suggest black holes do emit radiation. This is thermodynamics meeting quantum mechanics at the edge of a black hole. He is surprised. He is annoyed. He wanted to prove Jacob Bekenstein wrong. Bekenstein argued in 1972 that black holes have entropy proportional to their surface area. Hawking thought this was nonsense. Entropy means disorder. How could something with no features have entropy? But Hawking's calculations betray him. Not only do black holes have entropy, they radiate. The temperature equals surface gravity divided by 8 pi, multiplied by Planck's constant, divided by twice Boltzmann's constant. For a solar mass black hole, that is 60 billionths of a Kelvin, freezing cold. But it is temperature. Real, measurable thermal temperature. And temperature means radiation. Sciama tells Martin Rees, another Cambridge physicist. Rees quivers with excitement. Word spreads through Hawking's inner circle like fire through dry grass. But Hawking does not publish yet. He wants to be certain. If you value documented quantum physics and cosmology like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. Also, this script is researched and factual, using sources from Nature, Volume 2, 48. Published March 1st, 1974. Physical Review Letters, published in 2021, confirming the area theorem observationally, and biographical memoirs of Fellows of the Royal Society, Volume 66 from 2019, documenting Hawking's life work. These are peer-reviewed sources from the Royal Society, MIT, and Direct Nature publication archives. Now back to the information. February 15th and 16th. Hawking wheels into the conference room. It is not Valentine's Day as legend sometimes claims. That meeting ran February 15th through 16th. Hawking presents his calculation. Black holes emit radiation. They have temperature inversely proportional to their mass. They evaporate. For a black hole of 1 billion kilograms, evaporation time is 10 billion years. For smaller primordial black holes formed in the early universe, less than 1 billion kilograms, evaporation happens faster than the age of the universe. These black holes explode. Hawking is threatening to overturn everything they know about black holes. Roger Penrose is there. Brandon Carter is there. These are titans of relativity theory. Some are skeptical, some are confused, but Dennis Sciama backs Hawking completely. Sciama calls it a work of genius. March 1st, 1974, Nature publishes the paper. Title: Black Hole Explosions, Volume 2, 48, number 54, 43, pages 30 through 31, 2 pages, 152 lines. The most important result in fundamental physics in decades compressed into a letter. The paper opens with quantum gravitational effects. Hawking argues that quantum effects add up over the lifetime of the universe, 10 to the 17th seconds. Black holes create and emit particles as if they are hot bodies with temperature kappa over 2 pi times Planck's constant over 2 times Boltzmann's constant. Kappa is surface gravity. The formula stands. Hawking has shown that black holes violate the classical law that their event horizon area can never decrease. But he proposes a generalized second law. Total entropy never decreases if you add black hole entropy to matter entropy outside. The black hole entropy equals 1/4 of the horizon area measured in Planck units. This equation unites general relativity, quantum mechanics, and thermodynamics. 3 pillars of physics meeting at one point. In flat spacetime, virtual particle-antiparticle pairs appear and disappear constantly. They borrow energy from the vacuum for a fleeting instant allowed by Heisenberg's uncertainty principle. Near a black hole event horizon, one particle falls in with negative energy relative to a distant observer. The other escapes as real radiation. The black hole loses mass equal to the energy of the escaped particle. Mass and energy connect through Einstein's equation E equals mc squared. The black hole shrinks. A black hole with the mass of Earth's moon, 45 times 10 to the 22 kilograms, has temperature 2.7 Kelvin. That matches the cosmic microwave background. It neither gains nor loses mass. A solar mass black hole has temperature 10 to the negative 6 Kelvin. It absorbs far more cosmic microwave background radiation than it emits. It grows. But a primordial black hole with mass less than 10 to the 15 grams evaporates completely before now. A black hole in its final second releases energy at 10 to the 29 ergs per second. The last tenth of a second is an explosion. This is why Hawking titled the paper Black Hole Explosions ? If primordial black holes formed in the Big Bang, astronomers might detect their final bursts. 50 years later, no explosion has been observed. Detector search. The Ice Cube Neutrino Observatory watches for signals. Nothing yet. Either primordial black holes are rarer than expected, or they are slightly more massive than the evaporation threshold. Quantum mechanics says information cannot be destroyed. The wave function evolves by unitary operators. You can run physics backward. Initial state determines final state. But Hawking radiation is thermal. It is random. It carries no information about what fell into the black hole. Two different stars collapse to form black holes of the same mass. They radiate identically. When they evaporate, the radiation is indistinguishable. The initial states were different. The final states are the same. Information vanished. Hawking framed it as breakdown of predictability and gravitational collapse. He argued information is lost, published this argument in 1976 in Physical Review D. The physics community divides. Some accept information loss, others reject it as impossible. John Preskill at Caltech insists information must escape somehow. Quantum mechanics cannot be wrong. Leonard Susskind at Stanford agrees. Gerard at Hooft proposes the holographic principle. Information encodes on the event horizon like a hologram. The black hole interior is not separate from the exterior. It is encoded on the boundary. The stakes are an encyclopedia of the winner's choice. The wager sits unresolved for 13 years. ADS CFT duality. It suggests black holes in certain spacetimes are equivalent to quantum field theories at non-zero temperature. If true, information cannot be lost because quantum field theory forbids it. The holographic principle gains support. Spacetime might be emergent from a lower dimensional description on the boundary. It escapes via subtle correlations in Hawking radiation that his original calculation missed. He gives Preskill a baseball encyclopedia. Thorne refuses to concede and does not sign off on the bet resolution. Hawking's proposed mechanism involves information stored in supertranslations on the event horizon. Soft hair. The horizon geometry encodes data about what fell in. The radiation carries this imprint outward, but the mechanism is not detailed. Many physicists remain unconvinced. The paradox persists. 2007. Samir Mathur at Ohio State proposes fuzzballs. Black holes are not empty interiors surrounded by event horizons. They are balls of strings from string theory packed tightly with a surface radiating like a star. No information is lost because there is no event horizon trapping it. Information sits in the fuzzball structure. Hawking radiation is ordinary thermal radiation from the surface. No paradox. But fuzzballs require string theory to be correct and remain speculative. Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully published the firewall paradox. They argue that if information escapes in Hawking radiation, quantum entanglement requirements force a firewall of high-energy particles at the event horizon. An infalling observer hits the firewall and burns up. This contradicts general relativity, which says nothing special happens at the horizon to a freely falling observer. New paradox. The field erupts. Dozens of papers pour out weekly. Black hole complementarity. Information both falls in and reflects out, but no observer sees both, comes under attack. Information is temporarily trapped, but eventually escapes as space-time fluctuates. The paper has no equations. It summarizes remarks he made via Skype at a conference. The physics community debates its meaning. Some see it as radical rethinking. Others see it as vague and unconvincing. 2016. Hawking collaborates with Malcolm Perry at Cambridge and Andrew Strominger at Harvard. They publish a paper on soft hair. They argue massless particles called soft photons and soft gravitons surround black holes and preserve information. These particles have zero energy as measured at infinity, but carry angular information distinguishing black holes formed from different initial states. The soft hair entropy matches the Bekenstein-Hawking entropy formula. This provides a mechanism for information storage. The paper is Hawking's last major scientific contribution before his death. The equation shows temperature equals Planck's constant times the speed of light cubed divided by 8 pi times Newton's gravitational constant times the black hole's mass times Boltzmann's constant, 10 characters. This formula links gravity, quantum mechanics, and thermodynamics in one expression. It is one of 3 equations defining 20th century physics alongside Einstein's field equations and Schrödinger's wave equation. He trained students who became leaders in cosmology. He wrote A Brief History of Time, which sold 10 million copies and brought black holes to popular consciousness. He appeared on television shows. He advised on science fiction films. He became the public face of theoretical physics, despite being trapped in a wheelchair and unable to speak except through a voice synthesizer. His persistence inspired millions. Physics has moved forward. 2019, Jeff Pennington at Stanford, Ahmed Almhairi, Netta Engelhardt at MIT, Donald Merolf, Henry Maxfield, and others calculate the page curve using quantum extremal surfaces. The page curve shows how information initially increases in Hawking radiation, then decreases back to 0 when the black hole evaporates completely. This matches unitarity. Don Page predicted this curve in 1993, but no one could derive it from first principles. Pennington and collaborators do it using holography and quantum corrections to the geometry. The surfaces lie inside the event horizon. Their area measures the entropy of radiation that has already escaped, plus the black hole's remaining entropy. As the black hole evaporates, the quantum extremal surface shrinks. Eventually, it jumps to a surface just inside the horizon. Information floods out. The page curve is reproduced. The papers are published in Journal of High Energy Physics. This is considered a major breakthrough. Whether they extend to real 4-dimensional black holes in our universe is unclear. The mechanism by which information encodes in radiation remains abstract. No one can point to specific particles and say this particle carries this bit of information. The unitarity is restored mathematically, but the physical picture is murky. 50 years after Hawking's Nature paper, physicists at MIT and Cornell observed the first experimental confirmation of Hawking's area theorem using gravitational waves. July 1st, 2021, Physical Review Letters publishes the result. Maximiliano Eisi at MIT, Will Farr at Stony Brook, Matthew Giesler at Cornell, Mark Scheel at Caltech, and Saul Tucholsky at Cornell reanalyzed gravitational wave signal GW 150,914. This is the first gravitational wave detection ever made by LIGO on September 14, 2015. 2 black holes merged. The team calculates the horizon area before and after the merger. If Hawking's area theorem holds, the total area cannot decrease. They confirm with 95% confidence that the area did not decrease. Hawking's theorem passes its first observational test. The in-spiral before the merger, the ring down after the merger. From the in-spiral, they calculate the mass and spin of the 2 original black holes. They compute the horizon area of each using the formula for a rotating Kerr black hole. The area equals 4 pi times the quantity mass squared plus square root of mass to the 4th minus angular momentum squared. Sum the 2 areas. From the ring down, they calculate the mass and spin of the final black hole. Compute its area. Compare. The final area is larger. The theorem holds. LIGO continues operating. More black hole mergers are detected. Each one provides another test. The area theorem is confirmed repeatedly. Hawking's insight from 1971 that black hole horizon area never decreases is proven observationally 5 decades later. Einstein's general relativity holds, but the quantum corrections Hawking discovered in 1974 remain undetected. Hawking radiation from astrophysical black holes is too weak. A solar mass black hole radiates at 10 to the negative 28 watts. The cosmic microwave background alone delivers far more power. Detecting Hawking radiation from real black holes is impossible with current technology. They fire a laser pulse through glass, creating a moving refractive index that mimics an event horizon. Photons on one side cannot catch up. They measure photons emitted at the boundary. The spectrum matches Hawking radiation predictions. Other teams disagree whether it is truly Hawking radiation or a different effect. The debate continues. He creates a flow of atoms faster than the speed of sound in the condensate. This forms a sonic horizon. Phonons, sound quanta, on one side cannot escape. He runs the experiment 4,600 times over 6 days. He detects phonon pairs appearing at the horizon. High energy pairs are entangled. Low energy pairs are not. This matches Hawking's prediction. The thermal distribution of phonons confirms black holes radiate. The paper is published in Nature Physics. They tune the hopping ease to create a type of event horizon interfering with electron waves. They observe a temperature rise matching theoretical Hawking radiation, but only when part of the chain extends beyond the horizon. They suggest entanglement of particles on the horizon generates the radiation. This supports the idea that Hawking radiation requires quantum entanglement between interior and exterior regions. They probe the mathematical structure. If the same quantum field theory applies, the analogs should behave like real horizons. They do. This increases confidence in Hawking's calculation, even though direct detection remains impossible. But a different confirmation path exists. Primordial black holes. If micro black holes formed in the early universe with mass around 10 to the 11th kilograms, they would be exploding now. The final burst releases gamma rays. Detectors search the sky. The Fermi Gamma Ray Space Telescope monitors bursts. IceCube looks for neutrinos from explosions. So far, nothing. This constrains how many primordial black holes could exist. They are either very rare or non-existent. This does not disprove Hawking radiation. It constrains primordial black hole formation models. Another approach uses gravitational waves. Black holes merge throughout the universe. Each merger emits gravitational waves carrying information about the black hole's properties. As detectors improve, they might detect quantum corrections to the waveforms. These corrections would encode information about Hawking radiation and quantum hair. The challenge is that the corrections are tiny. Current detectors cannot see them. Third-generation detectors like Einstein Telescope in Europe and Cosmic Explorer in the United States might reach the needed sensitivity. These detectors are planned for the 2030s. Xavier Calmet at University of Sussex, Roberto Casadio at University of Bologna, Stephen Hsu at Michigan State, and Volker Kuipers published 2 papers, Physical Review Letters and Physics Letters. B. They show black holes have quantum hair. This is not Hawking's soft hair from 2016. It is quantum gravitational corrections to the black hole's field that encode formation history. The gravitational field itself at quantum scale carries information about how the black hole formed. This quantum hair provides the mechanism for information storage. The information escapes in Hawking radiation through correlations imprinted by the quantum hair. The papers claim this solves the information paradox without requiring speculative, new physics. General relativity and quantum mechanics combine consistently. The field remains divided. Some accept the quantum hair solution. Others point to unresolved issues. The calculations assume certain approximations. The black hole must be nearly stationary. The quantum corrections must be small. Whether these assumptions hold during the violent evaporation phase is unclear. The final moments when the black hole approaches Planck mass require full quantum gravity. No one has that theory. Hawking's discovery exposed the gap between general relativity and quantum mechanics. General relativity describes gravity as curved space-time, smooth, continuous, deterministic. Quantum mechanics describes particles and fields as probabilistic and discrete. These frameworks clash at black hole horizons and at the Big Bang singularity. A complete theory of quantum gravity would unite them. String theory attempts this. Loop quantum gravity attempts this. Causal dynamical triangulations attempt this. None are proven. Hawking spent his career probing this boundary. His 1974 calculation used semi-classical gravity, quantum fields on a classical curved background. This approximation works when gravitational fields are weak compared to Planck's scale, but strong enough to curve space-time significantly. At black hole horizons, this regime applies, but deep inside the black hole near the singularity, semi-classical approximation breaks down. Space-time curvature reaches Planck density. Quantum fluctuations of space-time itself become important. Hawking knew this. He knew his calculation was incomplete. But it was enough to reveal that black holes are thermodynamic objects. Entropy measures the number of microstates consistent with the macroscopic properties. What are the black hole's microstates? Hawking could not answer. String theory offers one answer. For certain extremal black holes, those with maximum charge for their mass, string theory counts the microstates. Brains and strings wrapping in extra dimensions. The count matches the Bekenstein-Hawking entropy exactly. This is a triumph for string theory, but it works only for special black holes. Astrophysical black holes are not extremal. The microstate counting for generic black holes remains unknown. Loop quantum gravity offers another answer. It proposes space-time is discrete at Planck scale. The event horizon is woven from quantum threads. Each thread contributes 1 unit of area. The entropy counts the ways these threads can be arranged. The calculation reproduces Bekenstein-Hawking entropy with the correct numerical factor. But loop quantum gravity struggles to connect to low-energy physics. It predicts modifications to general relativity at large scales. Observations so far show no deviations. The theory remains speculative. So 50 years after Hawking's discovery, the deepest questions remain open. Information loss or information preservation? What are black hole microstates? What is quantum gravity? Physicists have made progress. The Page curve is derived. Quantum extremal surfaces are identified. Quantum hair is proposed. But the complete picture eludes us. Hawking knew this. His 2016 paper on soft hair ends with the statement that the information paradox remains unsolved. He acknowledged the mechanism was not fully understood. He proved black holes are not cold, dead objects. They glow, they evaporate, they connect to thermodynamics through entropy. His formula S equals A over 4 in Planck units stands unchallenged. The temperature formula T equals surface gravity over 2 pi times. Planck's constant over Boltzmann's constant stands unchallenged. These equations bridge 3 areas of physics that seemed unrelated. They hint at a deeper unity. The road from September 1973 in Krakow to March 1st, 1974 in Nature is 24 weeks. In those 24 weeks, Hawking ran calculations, questioned results, checked equations, and arrived at a formula that redefined black hole physics. The speed is astonishing. He was working without modern computers. He was working while his body deteriorated. He was working because the problem obsessed him, and he delivered. 24 hours before he presented at Rutherford Laboratory on February 15, 1974, Hawking knew he would shock the room. He knew physicists would resist. He knew the result was correct. He had Dennis Sciama's backing. He had the equations. The formula was undeniable. Black holes radiate. He entered that conference room with a discovery that would define his career and shape physics for 50 years. The night before the announcement, February 14, 1974, Hawking would have been reviewing the presentation in his mind, running through objections, checking the derivation one more time. He would have known that some in the audience would reject it outright. Roger Penrose had proven black holes must have singularities. John Wheeler coined the term black hole in 1967 to capture their absolute darkness. Now Hawking was saying they glow, they evaporate, they explode. This contradicted intuition. It contradicted the name itself. But Hawking had the calculation. He had worked through the quantum field theory and curved space-time for a collapsing star. He had traced the particle modes from early times when the star was still large through the collapse to late times when the black hole settled into a stationary state. He had found that outgoing modes at late times correspond to positive frequency with respect to the time coordinate at infinity. These are real particles. The spectrum is thermal. The temperature depends only on surface gravity. The calculation was airtight. What Hawking could not have known that night is that his formula would outlast him. It would be engraved in stone at Westminster Abbey, where Newton and Darwin are also honored. It would inspire generations of physicists. It would launch fields of research that continue today: quantum information, holography, black hole thermodynamics, the firewall paradox, fuzzballs, quantum extremal surfaces, islands in the Hawking radiation. All of these trace back to that calculation in late 1973. Black holes are the simplest objects in general relativity. They have only mass, charge, and spin. No hair, as John Wheeler said in the 1960s. Yet when quantum mechanics enters, they become thermodynamic systems with entropy and temperature. This suggests thermodynamics is more fundamental than we thought. It suggests information is physical in a deeper sense. It suggests space-time itself might be emergent from quantum information. These are ideas Hawking helped pioneer. And the information paradox forces us to confront the nature of reality. If information is truly lost in black holes, quantum mechanics is wrong. If information escapes, general relativity must be modified. Either a fundamental law of physics breaks, or our understanding of black holes is incomplete. Hawking leaned toward information loss for decades. He was willing to abandon unitarity. Most physicists were not. The debate raged. In the end, Hawking conceded, but without a fully convincing mechanism for information escape. The paradox persists. Recent work suggests information does escape through subtle quantum correlations. The calculations using holography and islands reproduce the page curve, but the physical mechanism remains abstract. We do not understand how a particle emitted today as Hawking radiation carries information about a star that collapsed 1 billion years ago. The information must be scrambled almost beyond recognition, yet still recoverable in principle. Black holes are the fastest scramblers in nature. They randomize information on a timescale set by the inverse temperature, for a solar mass black hole that is 10 microseconds. Everything that falls in is mixed thoroughly and nearly irreversibly. Yet, quantum mechanics insists the process is reversible if you wait long enough and capture all the radiation. His discovery in 1974 was not the end. It was the beginning. It opened black hole thermodynamics. It revealed that quantum gravity has observable consequences. It connected 3 areas of physics in one equation. And it forced physicists to take information seriously as a physical quantity. We propose quantum hair and soft hair and fuzzballs and firewalls. We debate holography and adds CFT and the emergence of spacetime. All of this stems from one calculation by one physicist who refused to accept that black holes are perfectly black. Stephen Hawking died March 14, 2018. His ashes are interred at Westminster Abbey between Isaac Newton and Charles Darwin. On his memorial stone is the formula for black hole temperature. Not the full derivation, just the result. 10 characters. The temperature equal to Planck's, constant times. The speed of light cubed divided by 8 pi times Newton's gravitational constant times the black hole mass times Boltzmann's constant. This formula says that black holes glow, that quantum mechanics and gravity meet at the horizon, that information matters, that thermodynamics is universal. On the cover, punch holes in the inner margin. Inside, the calculation that changed physics. The last line of the paper says, the emission of Hawking radiation violates the classical law that black hole area never decreases, but a generalized second law holds when black hole entropy is included. 17 words, they contain a revolution. We have the area theorem confirmed by gravitational waves. We have the principle that black holes are thermodynamic objects. And we have the knowledge that one man in a wheelchair with a broken body and an unbreakable mind looked at the universe and saw what no one else could see. In late November 1973, Hawking was running calculations. By mid-December, he knew the answer. By early January, he was preparing the presentation. By February 15th, he announced it. By March 1st, it was published. The timeline is tight. The work is dense. The implications are vast, and at the center of it all is a formula that says even the darkest objects in the universe shine. It proves that nothing is truly black. And it came from 24 hours of mental preparation before a physicist wheeled into a room and told his colleagues that everything they knew about black holes was incomplete. The calculations were ready. The objections were anticipated. The result was correct, and physics would never be the same. He had 12 years left before losing his voice entirely. He had 44 years left before death. But on that night, he had the calculation that would make him immortal. Black holes radiate. The proof was complete. The announcement was hours away. But before Hawking's breakthrough, there was groundwork. 1971, Yakov Zeldovich and Alexei Starobinsky in Moscow showed that rotating black holes amplify quantum vacuum fluctuations. They used analogy with spinning metal spheres in electromagnetic theory. The rotation extracts energy from the black hole's spin. The ergosphere, the region outside the horizon where space-time drags, facilitates particle creation. This was called the Zeldovich effect. Particles emerge from the vacuum without violating classical physics because the rotational energy provides the source. But this only works for rotating black holes. Non-rotating black holes should remain dark. He argues black holes must have entropy. His reasoning comes from thermodynamics. Drop a hot object into a black hole. The object's entropy vanishes from the observable universe. The second law of thermodynamics says total entropy never decreases. Therefore, the black hole must gain entropy to compensate. Bekenstein proposes black hole entropy equals 1/4 of the horizon area in Planck units. This is order of magnitude reasoning. The exact coefficient is uncertain, but the principle is clear. Area measures entropy. Bekenstein presents this at a conference. Hawking is in the audience. Hawking objects strenuously. He argues that entropy implies temperature. Temperature implies radiation. Black holes, by definition, cannot radiate. Therefore, black holes cannot have entropy. Bekenstein's proposal must be wrong. The debate is heated. Bekenstein holds his ground, but Hawking is not convinced. He returns to Cambridge, determined to prove Bekenstein wrong. Hawking hears about Zeldovich's work through Douglas Erdley, a postdoc at Caltech, who learned about it from William Press and Saul Tucholsky. The Soviet result on rotating black holes is spreading through the Western physics community. Hawking decides to visit Moscow. He attends the International Conference on Gravitation and Relativity. This is where he meets Zeldovich and Starobinsky. They explain their calculation in detail. Hawking realizes the spontaneous emission from rotating black holes is real, but he wants to put it on firmer theoretical footing. Back in Cambridge, Hawking begins the calculation that will change everything. He does not just analyze rotating black holes, he tackles the full problem of a star collapsing to form a black hole. He uses quantum field theory in the curved space-time background. The key is to trace how quantum field modes evolve through the collapse. Early times, when the star is still large, define the incoming vacuum state. Late times, when the black hole has formed, define the outgoing particle states. The relationship between early and late time modes determines the particle creation rate. At very late times, the black hole is nearly stationary. He can match the solutions in these asymptotic regions. The matching reveals that what looks like vacuum at early times contains particles at late times. This is the Hawking effect. This is the stunning result. Not just any particles. A perfect blackbody spectrum with temperature inversely proportional to black hole mass. The thermality comes from the event horizon geometry. The horizon acts as a one-way membrane. Virtual particle pairs near the horizon separate. One partner falls into the hole, the other escapes to infinity. The escaping particles form a thermal bath when viewed by a distant observer. The temperature is set by surface gravity at the horizon. Temperature equals surface gravity kappa divided by 2 pi multiplied by Planck's constant divided by Boltzmann's constant. For a Schwarzschild black hole with no rotation or charge, surface gravity equals 1 over 4 mass in geometric units, where Newton's constant and speed of light equal 1. Restore physical units, and the temperature formula becomes explicit. For a solar mass black hole, mass equals 2 times 10 to the 30 kilograms. The temperature is 60 nanokelvin, incredibly cold, but real. It contains every fundamental constant of nature: Planck's constant from quantum mechanics, Boltzmann's constant from thermodynamics, Newton's gravitational constant from gravity, the speed of light from relativity. These constants never appear together in classical physics. Their combination in one formula signals that Hawking has touched something profound. He has found a place where quantum mechanics, thermodynamics, and gravity meet necessarily. If black holes have temperature, Bekenstein was right about entropy. The entropy is exactly 1/4 of the horizon area measured in Planck units. The coefficient that Bekenstein could only estimate by order of magnitude falls out precisely from the thermal spectrum calculation. Hawking has to admit Bekenstein was correct. This is difficult. Hawking wanted to disprove Bekenstein. Instead, he has confirmed the result and made it quantitative. The area-entropy relationship is exact, aber Hawking entdeckt noch etwas. Die Strahlung führt dazu, dass das schwarze Loch Masse verliert. Mit abnehmender Masse steigt die Temperatur, die Verdampfung beschleunigt sich. Schließlich verschwindet das schwarze Loch. Bei kleinen primordialen schwarzen Löchern geschieht dies in weniger als dem Alter des Universums. Für ein schwarzes Loch mit einer Masse von 10 hoch 15 Gramm beträgt die Lebensdauer 13 Milliarden Jahre. Das Universum ist fast 14 Milliarden Jahre alt. Wenn solche schwarzen Löcher im Urknall entstanden sind, explodieren sie jetzt. Deshalb betitelt Hawking die Arbeit Black Hole Explosions Fragezeichen. Das Fragezeichen ist wichtig. Hawking schlägt etwas vor, das beobachtbar überprüfbar ist. Primordiale schwarze Lochexplosionen würden Gammastrahlen freisetzen. Detektoren könnten nach diesen Ausbrüchen suchen. Das Fragezeichen besagt, dass dies eine Vorhersage ist, nicht nur Theorie. 50 Jahre später wurden keine Explosionen gefunden. Dies widerlegt die Hawking-Strahlung nicht. Es schränkt ein, wie viele kleine primordiale schwarze Löcher existieren. Sie müssen selten sein, oder die Massenverteilung muss über dem Verdampfungsschwellenwert ihren Höhepunkt erreichen. Und eine längere, detaillierte Arbeit für Communications in Mathematical Physics, die die vollständige Berechnung ableitet. Er reicht die längere Arbeit im März 1974 ein. Die Zeitschrift verliert das Manuskript. Ein Jahr später erkundigt sich Hawking nach dem Status. Sie bitten ihn, es erneut einzureichen. Die Arbeit wird schließlich 1975 veröffentlicht, wobei das Einreichungsdatum fälschlicherweise als April 1975 angegeben wird. Dies führt zu Verwirrung über die Priorität. Die Nature-Arbeit, die am 1. März 1974 veröffentlicht wurde, belegt, dass Hawking das Ergebnis zuerst im Februar angekündigt und zuerst im März veröffentlicht hat. 2 Seiten. Er legt das Schlüsselergebnis dar. Schwarze Löcher emittieren thermische Strahlung mit einer Temperatur, die proportional zur Oberflächengravitation ist. Die Implikationen für die Thermodynamik schwarzer Löcher und für den Nachweis primordialer schwarzer Löcher werden umrissen. Die längere Arbeit liefert die Ableitung. Sie führt durch die Quantenfeldtheorie in gekrümmter Raumzeit. Sie zeigt, wie die Bogolyubow-Koeffizienten berechnet werden, die frühe und späte Teilchendefinitionen in Beziehung setzen. Sie beweist, dass das Spektrum exakt thermisch ist. Sie diskutiert den verallgemeinerten zweiten Hauptsatz, der Materie-Entropie und Schwarzes-Loch-Entropie kombiniert. Martin Rees sagt, alles habe sich geändert, aber andere sind skeptisch. Die Berechnung verwendet die semiklassische Näherung. Vielleicht würde die vollständige Quantengravitation das Ergebnis ändern. In den nächsten Jahren leiten andere Physiker die Hawking-Strahlung mit unterschiedlichen Methoden neu ab. William Unruh in British Columbia zeigt, dass derselbe Effekt bei beschleunigten Beobachtern in flacher Raumzeit auftritt. Der Unruh-Effekt bestätigt Hawkings Ergebnis. Ende der 1970er Jahre wird die Hawking-Strahlung als Standardphysik schwarzer Löcher akzeptiert. Dies widerspricht der Quantenmechanik. Hawking argumentiert 1976, dass die thermische Natur Information zerstört. Dies entfacht jahrzehntelange Debatten. Gerard 't Hooft schlägt 1993 vor, dass alle Information auf der Ereignishorizontgrenze kodiert ist. Leonard Susskind entwickelt dies zum holographischen Prinzip. Juan Maldacena beweist es 1997 mit der Anti-de Sitter-konforme Feldtheorie-Korrespondenz. In diesem Rahmen bleibt Information erhalten, aber Hawking bleibt jahrelang unüberzeugt. Don Page sagt 1993 die Page-Kurve voraus. Die Strahlungsentropie sollte zunehmen und dann wieder auf Null abnehmen. 2019 leitet Geoff Pennington dies mit Hilfe quantenextremer Oberflächen ab. Ahmed Almheiri, Netta Engelhardt, Donald Marolf und Henry Maxfield kommen unabhängig voneinander zum gleichen Ergebnis. Information fließt durch Quantenverschränkung. Der Mechanismus bewahrt die Unitarität. Ende 2024 zeigt eine neue Analyse von Netta Engelhardts Team am Massachusetts Institute of Technology, dass die quantenextremen Oberflächen, die die Hawking-Strahlung erfordert, nicht genauso entstehen können, wie Hawking es in seiner ursprünglichen semiklassischen Näherung berechnet hat. Die Oberflächen benötigen Quantenkorrekturen, die Hawking 1974 nicht einbeziehen konnte. Sein Ergebnis ist korrekt, aber unvollständig. Das Gesamtbild erfordert Quantengravitation. 50 Jahre später entpacken wir immer noch, was Hawking in diesen 24 Wochen von Krakau nach Cambridge zu Doerr, Nature entdeckt hat. Die Formel funktioniert, der Mechanismus vertieft sich, das Paradoxon dauert an. Und die Frage, die Hawking Ende 1973 stellte, strahlen schwarze Löcher, treibt die Physik heute noch an, denn die Antwort ist ja, und wir verstehen immer noch nicht vollständig warum.